In this video, we are going to find integers x, y, and z such that x minus yz equals 11 and xz plus y equals 13. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. The trick to solve this system of equations is simple. We can square both sides of both equations and add them up. So we have x minus yz all squared plus xz plus y all squared equals 11 squared plus 13 squared. Then expanding the left side, we have x squared minus 2xyz plus y squared z squared plus x squared z squared plus 2xyz plus y squared. And then the right side is equal to 290. The reason that I do this is that by squaring x minus yz and xz plus y, we have terms that includes all three variables x, y, and z, which are over here. What's more is that one is a plus 2xyz and the other is minus, and if we add them up, they actually cancel out. So now we have something achieved from the two equations that looks a little better than the form we are given. More importantly, we have made use of the symmetry between the three variables. Another good thing that happens on the left side of the expression at the current step is that we can factorize the four terms. In fact, we can group the four terms in this way. The green group can factorize into z squared times x squared plus y squared. And then we can add the yellow group. And we also have a common factor of x squared plus y squared. And this expression multiplied by z squared plus 1 is equal to 290. So now we've factorized the left side. Next, because x, y, z are supposed to be integers, that means z squared plus 1 being positive is a factor of 290. So that means z squared plus 1 is either equal to 1, 2, 5, 10, 29, 58, 145, and 290. There should be 8 factors because 290 is equal to 2 times 5 times 29. So the number of factors should be the product of each exponent added by 1. Which means there are 8 factors, and we have included all of them. So now we can solve for z. So z squared is equal to either 0, 1, 4, 9, 28, 57, 144, or 289. And only these two cases, 28 and 57, will not give integral solutions. For the others, we have z equals 0, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 12, and plus or minus 17. Now it remains to solve for x and y. Given that we have solved for values of z, if we put them one by one into our given system, then we actually have two equations, two unknowns. By rewriting the system that we are given, we can actually solve for x and y in terms of z, treating z as a constant. If I multiply the first equation by z, then we have xz minus yz squared equals 11z. So we have the third equation. Now, we can subtract the second equation by the third equation. And now for the left, the xz term vanishes, and so we have y times 1 plus z squared, and that equals 30 minus 11z. Since for the values of z we have obtained, z squared plus 1 are all non-zero, so we can safely divide both sides by z squared plus 1. And we have y equals 30 minus 11z over z squared plus 1. Now we can solve for x as well. And in fact, x equals 11 plus 13z minus 11z squared over z squared plus 1. Then we can simplify the expression, and we have 13z plus 11 over z squared plus 1. So from this, let me copy that above. So I can scroll back up and deal with each value of z one by one into our order pair of x and y. So now by putting in, say, z equals 0, then we have x equals to 11, y equals to 13, and z equal to 0. Next, when z equals plus or minus 1, then we have first 12, 1, 1, minus 1, and also 12. For the remaining values of z, the order pairs are that's the two order pairs for z equals plus or minus 2. You may notice that when z equals 2, x and y are not integers. It's possible. So I have to reject some of these cases. So not all of them are solutions. Now we can move on to other order pairs when z equals plus or minus 3, plus or minus 12, and plus or minus 17. We still have to reject order pairs when z equals minus 3 and 12, whereas for z equals 17 or minus 17, x and y are also between minus 1 and 1, as in the numerator is more than the denominator. Finally, this triple for minus 17. So we have to reject both order triples at last. And so those ticked are valid solutions. And there are altogether 6 of them. So this is the final answer. Please feel free to share your ideas in the comments. Thank you for watching. See you next time.